All right, so this is question 3 of homework 6. And in this one, it's a little bit different. We're just working with a lot of weird reaction forces. So we have this kind of strange mechanism with like a slider here that is being pushed on here. So there will be some reaction force this way, and then that'll, cause reactions here, which will cause reactions here, etc., etc. And so the problem asks us to find all the components of forces acting on the member ABE, which is this bar right here. So what we can do right away is we can draw a free body diagram of the entire thing, just as a rigid body. So we'll do that real quick. So here we have E, F, and then up here there is the 12 kilonewton force. And then I'll just define my coordinates as well. And then my distances. 1.2 meters, and then over here we have 0.9 meters, 0.9 meters, and 0.3 meters to point D. Okay? If we look at the picture, we see that E is a pin and F is also a pin support. So they will both have X and Y components. So we'll draw it out like this. And then we can do we can use moment equations to find some of these forces immediately just from this free body diagram. So if we take the moment about point E, right here, we can then find the forces actually just Fy. Because this cancels out, this cancels out, this cancels out, and then the 12 kilonewtons and the Fy are the only things that we have to worry about. And the reason we're doing this is because we need to have Fy to be able to solve for Ey with the force equation. So sum of moments about E equals 0, and we have a counterclockwise Fy, which is positive. So 1.8 meters, which is this distance, times Fy, and then minus the 2.1 meters times this 12 kilonewtons. And that gives us our Fy, which is 14 kilonewtons upwards. So that'll be in the J direction. And then using a sum of moment in the, a sum of force in the Y direction, we get Ey plus Fy minus 12 kilonewtons is equal to 0. And then if we rearrange that, we get Ey is equal to 12 kilonewtons minus Fy, which we just solved for as 14 kilonewtons. And that'll give us negative 2 kilonewtons, meaning that Ey is pointing in the negative J direction or downwards. So we actually already solved for one of the forces that they're asking us for, because that is acting on member ABE. So from here, what we should look at is now the middle component, this BCD, because we want to find the reaction forces at B as well. So if we draw a free body diagram for that, member BCE, that'll look something like this, where we have D, it's actually BCD, my mistake, D, and then C is, we'll say it's here, and then B here. Now B is a reaction force. So it'll have, a pin support. So it'll have two reaction forces, one in the X, one in the Y. C is just like a roller kind of thing. So it will actually only have a force normal to member AF. But we can then decompose that into its X and Y components like this. And then at D, we have that 12 kilonewton load that was given to us. So from here, what we can do is we can take moment about B, and that'll allow us to isolate our CY component, because our CX component is going to go through the point and cancel out. And then all we have to worry about is our 12 kilonewtons and a CY. So let's see, B, C, D member. So moment about B is equal to 0. And we have all these distances, actually not quite. We need to use some geometry to find the distances. So we have this triangle 0.9 meters and then 0.6 meters. Or no, my mistake. 1.8 meters, which is the addition of these. And then we can use that to find this angle, and then use similar triangles to find the distance up to B, just by shrinking it down, basically. And so from here, we can find the distances on the BCD beam, and we get that from B to C is 1.2 meters, and we get from C to D is 0.6 meters. So now we can write out our moment equation. We have a counterclockwise CY thing, so that'll be positive. Whoops. So it'll be 1.2 meters times CY. And then our 12 kilonewtons is clockwise, so that'd be negative. So it'd be 1.8 meters times 12 kilonewtons. And then rearranging for CY, we get that CY is equal to 18 kilonewtons upwards or in the positive J direction. And then we actually have the constraints to find C of X from this. So we know that it is perpendicular to this triangle here. So the force C is going to be like this, right? And what we can do is take the angle. So this is kind of how I visualize it. So if we take this angle and then subtract it from 90, we get this angle, right? And that is how much the vertical, the Y component of this triangle tilts over. And then if we then take the perpendicular component here, this angle is going to be the same. So what we have basically is that we end up with, let's see, like this being the same. And that is equal to the internal angle here subtracted from 90. So theta is equal to 90 minus phi in this case. And so using that trigonometry, we can find Cx. Well, I'll just do that. So we have this triangle that is 0.9 meters and then 1.8 meters, same as the other one that way. And so using inverse tangent, we can find our phi. So we have inverse tangent of the opposite side over the adjacent side is equal to phi. And we get tangent of 1.8 divided by 0.9 is equal to 63.43 degrees. And then 90 degrees minus 63.43 degrees is equal to our theta here. And we get 26.57 degrees is our theta. And so if our CY component, I'll draw out the force now. So if our CY component is 18, we can slide it over here and then create a triangle with our X component. So we have CY, CX, C, or I can call it F at C. And then we have our angle as well, which is theta. And so our CX component is going to be CY times the, actually divided by tangent of theta. And we get that from tangent of theta is equal to CY over CX. And then, rearranging with algebra. And so now plugging that in, we get that C of X is equal to 36.0 kilonewtons. All right. And so now we can do sum of X and Y forces on the BCD member. And in the X direction, we have BX plus CX equals 0. And so we get that BX is equal to negative CX. And that is equal to, negative 36 kilonewtons in the I direction, or since it's negative, it's in the left direction. All right, and then sum of forces in the Y direction are equal to 0. So we get BY plus CY minus the 12 kilonewtons is equal to 0. And that gives us our BY, which is 6 kilonewtons downwards. And so that would be, oh my goodness, downwards in the negative J direction. And so now we have solved for 2 more forces in the question that it's looking for. So I'll highlight those. All right, and then we can draw, actually we can isolate the ABE component to find the rest of the forces. So I'll draw the FBD of ABE member. All right, so coordinates, and then A up to, or actually A is at the top, so A, E, and then B here. And then we have, let's see, 1.8, 6. So it would be 0.3 here from that geometry we used earlier. And then we have 0.6 up from here. And then across is 0.9 meters. I'll put meters as well. And then all the way up is 1.8 meters. Okay? And then if we look at the reaction forces on each of these pins, we have a pin here, and a pin here. So they're all going to have X and Y components. So we have AX, AY, BY, which we solved for, BX, we also solved for, EX, and EY, which we solved for. Okay? And from here, we only have 3 unknowns because we solved for these 3, and then EX, AX, and AY are unknowns now. So we can just use the force balance equations. We'll do a moment about A so that we can cancel out AY and AX and just look at EX. So moment about A equals 0. And then we have this 1.2 meters distance from here is the moment arm. Counterclockwise, clockwise, and then clockwise, counterclockwise. So we'll have the counterclockwise BX, and that is a 1.2 meter moment arm. And then the clockwise BY with a 0.6 moment arm. And then the EY will have a 0.9 moment arm, and it is clockwise as well. And then the EX is going to have a 1.8 moment arm counterclockwise. And then this is known, and this is known, so we can rearrange for EX. And we get that EX is equal to 23.0 kilonewtons to the left, or negative 23 kilonewtons in the I direction. All right, and then now all we're looking for is AX and AY. And so we can do sum of forces in the X and Y direction. So sum of forces in the X direction is equal to EX plus BX plus AY is equal to 0. Rearrange for for AX. And you get AX is equal to 36 kilonewtons to the left, so negative 36 in the I direction. And there you go. And then sum of forces in the Y direction. Y direction, okay, is equal to EY plus BY plus AY. Rearrange for AY. And finally, you get AY is equal to 4 kilonewtons down, or in the negative J direction. And there you go. That is problem 3. And I actually found a quick mistake that I wanted to fix. Since we drew the BY and BX direction in the positive coordinate axes in this free body diagram, the free body diagram for this component is going to have to be in the opposite direction because they are Newton reaction pairs. So they are equal opposite components. And then since this is the full system, it's okay because this is the same pin. But yeah, thank you.